Hello, this is still Ken, and we're still in lesson 2 of our course in mechanics on motion along a straight line. In this video, we're going to continue our discussion starting with acceleration, and then later we'll move forward to motions with constant acceleration. In the last video, I've left you some questions to check your understanding, and these are the answers to the questions. Pause the video to review your answers. Let us have a brief discussion on instantaneous velocity. The instantaneous velocity is the average velocity in the time limit as the time interval becomes infinitesimally short. In mathematical form, the instantaneous velocity is given as v is equal to the limit of delta x over delta t as delta t approaches to 0. Or this is also equivalent to the time derivative of dx over dt. The instantaneous velocity is the velocity at a specific instant of time or specific point along the path. For those of you who has no background in calculus, the instantaneous velocity meant about the velocity in an instant. Consider, for example, looking at the speedometer of a car. While traversing the road, you will see that the speedometer of the car is continuously moving. And if you want to find the instantaneous velocity, that is the velocity at the instant you laid your eyes on the speedometer. So that is the instantaneous velocity. We can also find or have a look on instantaneous velocity in your xt graph, or you have your displacement versus time graph. So at any point on an displacement time graph, the instantaneous velocity is equal to the slope of the tangent to the curve at that point. This is an example of an xt graph. So here you have your displacement versus your time graph. This blue curve here corresponds to your velocity curve. Okay. Now this is what we're actually doing when we're finding the average x velocity. Consider you have 2 points at some specific time, at time 1 and then at time 2. And if we want to find the average velocity at this point, we connect this one with 2 lines, and then the slope of this line is equal to the average velocity of these 2 points. Okay, but as the average x velocity is calculated over shorter and shorter time intervals, like say for example this one, okay, we have a shorter time interval from point 1 to point 2. The value of the average x velocity, you have your delta x over delta t approaches the instantaneous x velocity. If we are going to take the limit of your delta x over delta t to approach so that your delta t approaches to 0, like say for example at this point here, the instantaneous velocity at any given point equals the slope of the tangent to the displacement time curve. So we have this tangent line here, okay, tangent to this to the point along this curve, and the slope of this tangent line is equal to the instantaneous velocity. Now let's go to your average acceleration. The average acceleration or acceleration is the rate of change of velocity. In mathematical form, you have your acceleration along the x. This is equal to the rate of change of velocity. You have delta vx over delta t, which is equal to your v2 minus v1 over t2 minus t1. Again, your point 1 is your initial point, and then point 2 is your final point. The dimensions are length over time squared, so that means the SI unit for your acceleration is equal to meters per second squared. In one dimension, let's say for example motion along the x, your acceleration can be positive or negative, and your positive or negative sign can be used to indicate the direction. Like say for example you have positive acceleration, you can say that it moves along the x. If you have a negative acceleration, it moves to your negative x direction. However, there is a difference between negative acceleration and deceleration, because you might say that the negative acceleration in your calculation is, or it moves along the negative x-axis, or maybe that the negative in your acceleration meant deceleration of your body. Okay, negative acceleration is acceleration in the negative direction as defined by the coordinate system. Again, when we say it's a negative acceleration, it is the acceleration in the negative direction as defined by the coordinate system. So you may have your negative x or in your negative y axis. On the other hand, deceleration occurs when the acceleration is opposite in direction to the velocity. Again, deceleration occurs when the acceleration is opposite in direction to the velocity. So this means that your body is actually slowing down. It's not going faster. So it's what we call the deceleration. And it's different when we say you have negative acceleration versus your deceleration. Let us check your understanding. First question, if the velocity of an object is zero, does it mean that the acceleration is zero? For the second question, if the acceleration is zero, does it mean that the velocity is zero? Think of some examples. We will answer these questions in the next video. For now, let us have an example on the average acceleration. An automobile is moving to the right along a straight highway, which we chose to be the positive x-axis. Then, the driver puts on the brakes. If the initial velocity when the driver hits the brakes is 15 meters per second, and it takes 5 seconds to slow down to a velocity of 5 meters per second, what was the car's average velocity? Let us solve this problem. For this problem, we are given with the following quantities. We are given with the initial velocity v1, which is equal to 15 meters per second, and we are given with v2, which is equal to 5 meters per second, and then lastly, we're given some time, 5 seconds. For this problem, our target is the average acceleration. Now let us solve the problem. You know now that the average acceleration is equal to your delta v over your delta t, which is equal to your v2 minus v1 over your t2 minus t1. Your average acceleration is equal to 5 meters per second minus 15 meters per second divided by your time, 5 seconds. Your average acceleration then is equal to negative 2 meters per second squared. In the same concept with your instantaneous velocity, we also have this instantaneous acceleration, meaning the acceleration at an instant. The instantaneous acceleration is the limit of the average acceleration as delta t approaches to zero, or in mathematical form, we have ax is equal to the limit of delta vx over delta t as delta t approaches to zero. Or this is also equal to the time derivative of your velocity, or you have your dv over dt, or this is equal to the second time derivative of d squared x over dt squared. The term acceleration then will mean the instantaneous acceleration. This is the graphical representation of your instantaneous acceleration. You can find the acceleration on a velocity time graph. So consider this figure here. You have on your vertical axis the velocity, and on the horizontal axis you have your time. And the green curve here is your acceleration curve. When talking about the average acceleration for two specific points, like say for example at point 1 and then at point 2, the average acceleration is equal to the slope of the line connecting the two curves here. So you have this line here, and then you get the slope of this line. This is equal to the average acceleration. However, if we take the change in time to approach to zero, meaning you approach to smaller segments of your time, and we can say that we only have one point around here. Um, the slope of the line, which is tangent to this point in the curve, is equal to, or this is what we are referring to as the instantaneous acceleration. Let's have an example. The velocity of a moving car moving along the x-axis varies in time according to the expression v of t is equal to 40 meters per second minus 5t squared meters per second cubed, where t is in seconds. So in this problem, we're given with a velocity function in terms of t of 40 meters per second minus 5t squared meters per second cubed, where t is in seconds. A. Find the average acceleration in the time interval from time equals 0 to time equals 2 seconds. And B. Determine the acceleration at 2 seconds. In the first problem, you're given, or we are asked with the average acceleration. So our target is a average. Let's solve this problem. So since we are given with a function, we substitute at time equals 0 or your t equals 0 to the function, so that we have our v of 0 is equal to 40 meters per second minus 5 0 squared meters per seconds cubed. This is just 0. So at t equals 0, your v of 0 is equal to 40 meters per second. At time equals 2 seconds, your v of 2 is equal to 40 meters per second minus 5 2 squared meters per seconds cubed. Solving for this problem, your v of 2 is equal to 20 meters per second. Thus, the average acceleration is equal to, again, you have your v2 minus v1 over t2 minus t1. You have 20 meters per second squared minus 40 meters per second squared over 2 minus 0 seconds. Your average acceleration is equal to negative 10 meters per second squared. Now let's solve the second problem. Your second problem asked us to determine the acceleration at time equals 0. Let me erase this one first. Now, when we're talking about the acceleration, as we have stated earlier in our discussion, when we say acceleration, we are referring to the instantaneous acceleration. That means that is equal to the time derivative of your dv over dt. So let us solve the second problem. Okay, so for v, our target is the acceleration a. Your acceleration or your instantaneous acceleration is equal to dv over dt. So that means we need to find the time derivative of this function, 40 meters per second minus 5t squared meters per second cubed. Now, the derivative of a constant is 0, so this is just 0 here, and we just need to find the time derivative of negative 5 t squared meters per seconds cubed. The time derivative of this one is, you have negative 5 times 2 t meters per seconds cubed. Your average acceleration then at t equals 2 seconds is equal to negative 5 times 2 meters per seconds cubed. Or your acceleration, sorry, let me rewrite. Your acceleration is equal to negative 20 meters per second squared. You have your seconds here. Okay, it is it's just a square because your seconds here is cancelled by another second here. So you just have 2. So it's negative 20 meters per second squared. For those of you who has no background in calculus, you can left this part here. Now let us go to the motion with constant acceleration. When we say constant acceleration, it refers to the motion where the speed increases by the same amount each second. The most notable example is your free fall. In free fall, the acceleration is due to the acceleration due to gravity, which is equal to negative 9.8 meters per second squared. We have a negative acceleration because the acceleration due to gravity goes to your negative y-axis. It goes downwards. Other examples for motion with constant acceleration are a body sliding on an incline or on a rough horizontal surface, and an airplane being catapulted from the deck of an aircraft carrier. This is how your particle or your body moves if it goes with, or if it moves with constant acceleration. So it starts with a velocity v, and if the particle moves in a straight line with constant acceleration, the velocity changes by equal amounts in equal time intervals. However, the position changes by different amounts in equal time intervals because the velocity is changing. So here, your body moves faster and faster at the same constant acceleration, as seen also by the change in the position at each time interval. We have 4 equations used to describe motion with constant acceleration. In this section, you're going to derive these 4 equations. Again, for motion with constant acceleration, this is the case only for which velocity changes at the same rate throughout motion. We can start with the average acceleration formula. We have your average acceleration is equal to delta v over delta t, which is equal to your v2 minus v1 over t2 minus t1. This is the average acceleration along a straight line motion. Now, when the average acceleration for any time interval is the same as your a, we can replace your average acceleration equal to a. If that is the case, your average acceleration becomes just a, since the acceleration is the same for any time interval. Your a is equal to your delta v over delta t, which is equal to your v2 minus v1 over t2 minus t1. Again, we have this equation for your acceleration. And we're going to play with this equation. Now we'll let your initial time t1 equals 0. We can say that this is your 0 seconds. And at time 0, or at initial time t0, your v1 will represent it, or will let it as your v0, or your v sub 0. This one here is read as v0. It's spelled as NOUJGHT. It's not, or you can say it's v sub 0. We also let your time to t2 equals t to refer to any time later. And if that is the case, at any time later, your v2 is equal to v. Okay, we're going to use these expressions now to our equations above. So we're going to replace these terms here with all the quantities we have let here. If that is the case, your acceleration now becomes v minus v0 over t. Again, this is just from this equation here, and we let some of the expressions replace the terms here with these expressions, and your equations becomes a is equal to v minus v0 over t, or you can play with this equation by multiplying t both sides and moving some terms. You have your v is equal to v0 plus at. And we'll refer to this one as your equation 1. And as you can see, we've boxed this one because this is the first equation of motion for constant acceleration. So we need to find 3 more. We can also derive an equation for the position x as a function of time when the acceleration is constant. From this equation for your average velocity, and from our initial conditions, we let t1 again is equal to 0, and at initial time t0, or t sub 0, your x1 is equal to x0. And we let your t2 is equal to t to refer to any later time, and at any later time, your x2 is equal to x. From that, you're going to use these expressions here and substitute this one to this equation, and we get your v average is equal to x minus x0 over t. And we'll refer to this one as the equation 2. We can also get a second expression for v average that is valid only when the acceleration is constant. This is just your v average is equal to v0 plus v over t. And we'll refer to this one as equation 3. Take note that this equation is valid only for constant acceleration. Substituting equation 1 to equation 3, if you remember equation 1, we'll use that one and substitute it to equation 3 for your v. We have your v average is equal to v0 plus this one here. This is your equation 1 plus v naught plus 80 over 2. This is just 2v naught plus 80, or your v average, simplifying, is equal to v naught plus 1/2 80. And we'll refer to this one as equation 4. Next, we're going to set equation 4 and equation 2 equal. Setting equation 4 and equation 2 equal, we get your v naught plus 1/2 80. This is again your equation 4, equal to x minus x naught over t, your equation 2. And playing with this equation here, you get x equals x naught plus v naught t plus 1/2 80 squared. And we'll refer to this one as equation 5. Take note that we have boxed this equation again because this equation is your second equation of motion for constant acceleration. It is often useful to have a relationship for position, velocity, and constant acceleration that does not involve time. From equation 1, you have again your v is equal to v naught plus 80, and rewriting it in terms of t, your time is equal to v minus v naught over a. Substituting the resulting expression to equation 5, you have your equation 5 here, and these are your p expressions. So we get x is equal to x naught plus v naught times v minus v naught over a plus 1/2 a times v minus v naught over a squared. Simplifying the equation, we get v squared is equal to v naught squared plus 2a times x minus x naught. Please verify if indeed by playing with algebra of this equation makes it this equation here. And we'll refer to this one as equation 6. This is the third equation of motion for constant acceleration. We can get one more useful relationship by equating equation 2 and 3. Equating your equation 2 and 3, we get your x minus x naught is equal to v naught plus v over 2 times t. In summary, on the table are the 4 equations of motion used to describe motions with constant acceleration. Take note here that the sub x in the equations tells us that we are referring to the horizontal motion. In the next video, we're going to show some examples of how you're going to use these 4 equations of motion. See you!